Hello everyone, I'm back, and today I'm going to continue working on my CPU. I have quite a few things that I want to be working on today, so let's not get lost in words and let's start. So first of all, last time I created a sort of architecture roadmap, but more than a roadmap, it is really a few questions that I need to answer myself about what kind of architecture I want to build. So we are going to do that, but before doing that, actually, I want to create a new log file. Hello? Okay, yeah. I'm gonna call it log.md, and I'm gonna use that as a way to keep track during the weeks or months or however long this is going to be, this project. So I mean the various phases of this project and that I'm working on for each day. I think this is like beneficial for me to understand what I'm building during the days, and so I'm gonna do that. So maybe I can have like, I don't know, let's call this logbook, and maybe we can have an entry like this with as a double header with the day as the title. So today is I don't know, let me check, 22 of May. I'm gonna use the standard European way of writing dates. So 26. Do I wanna give it a title? Maybe, maybe not. Yeah, let's give it a title. Working, choosing architecture, let's say architecture choices. And then here I'm gonna write both what I want to and what I did, I guess. I don't know, like in bullet points. But I'm gonna do that later. So maybe now I can write what I want to do. So what do I want to do? For now I want to read through the plan that and the file to decide architectural choices about the CPU. Maybe after I have that, I guess I can also start working on something small which can be already implemented, because I want to get to some real hardware here. I have the board with me. It's here. It's the Basys 3, and maybe I can try to set up some code to see how it is working right now. But yeah, let's see. So start to write something and maybe test it. Okay. Yikes. Then let's go through the plan. This was a course generated by Gemini, which is now, it was Gemini Clee, now it's anti-gravity. But yeah, let's see what kind of questions. I asked it to generate some kind of questions which I think are which it thinks they're useful when creating a new CPU from scratch. Let's see if actually they make sense or if there are other questions that we should add. So this document contains key architectural questions to help guide the design of your 32-bit RISC-V CPU. Okay. Let's remove the bloat. Okay, memory architecture. Harvard versus von Neumann. So, Harvard separate instruction memory and data memory. It's easier to design for a single cycle or basic pipeline processors, because you can fetch an instruction and read-write in the exact same clock cycle without contention. So, this is the Harvard architecture. Otherwise, we have von Neumann. Shared memory for instruction and data, more realistic for a full system but requires a memory controller to arbitrate between instruction fetches and data accesses, often introducing stalls or requiring caches. This is certainly interesting. We'll start with separate instruction memory and data memory for simplicity, or immediately tackle a unified memory bus. I think for now I'm going to go for the Harvard architecture. Let's actually, so first of all, let me see which model here is selected. Let's go with the, oh, we have also cloud, I didn't know about that. Okay, since we are with Flash, let's keep using Flash. Get up to date code base, and then just me. No, actually, argue what are main differences. No, what are the main pros and cons of the Harvard versus von Neumann architecture. So I can put like an answer here. Yeah, like this. I think a Harvard architecture could be actually easier. Maybe von Neumann would be a bit overkill right now. But let's actually see. So yep. Harvard architecture, separate physical memory, yeah, we understood that. Pros, no structural hazards in the pipeline. In a classic five-stage pipeline, you must fetch an instruction and load stored data, the same clock cycle. Because paths are physically separate, they can happen simultaneously without conflicts or stalls. So I guess we want in a first stage something like that, but we want them to switch to a von Neumann architecture. Simpler CPU control logic. You do not need to implement complex memory arbitration, bus lock, or pipeline stall. FPGA resource efficiency. CPU cannot accidentally override executing code because the instruction space is not write accessible. Cons. Memory fragmentation. If your instruction memory is nearly full but your data memory is empty, you cannot use the data memory to store more code. Of course, program loading complexity. Since the CPU's data write instructions cannot write to the instruction memory, loading programs requires external hardware. What? Ah, yeah, true, cause... Yeah, but we don't have any other memory anyway, so... OS linker incompatibility. Modern operating systems and linkers assume a unified address space. It is very difficult to implement things like dynamic loaders, just-in-time compilers, or standard operating system page table schemes. A single unified physical memory space and bus. Unified address space. Simplified bootstrapping. A single memory bus means the CPU cannot read-write data and fetch a new instruction in the same cycle. High pipeline complexity. Since you're targeting the Basys tree, there is an excellent hybrid approach that is widely used in FPGA softcores. Xilinx block RAMs can be configured as true dual-port RAMs. This means the physical RAM block has two completely independent read-write ports that can access the same memory array simultaneously. You can configure a single unified memory block in your design, but connect port A to the instruction fetch stage and port B to the memory data stage. Software treats it as a von Neumann. You can load code and write data into the same address space. Hardware treats it as a hardware. But I do have a question, because yeah, it is true that we have two separate ports, but probably, I mean, they are accessing the same memory. So what happens if, for example, I'm accessing the same... Wait, if I have same memory but two different ports? But I still have the problem of stalls and a single memory issues. What happens if I read or write both ports to the same memory address? Is the memory inherently split between the two ports? We can actually see that here. Before doing that, actually, I want to do something else. I also want to create some documentation which maybe can be put in here, not sure. No, I can create a standalone folder called doc. It's already there. Okay. Let's call this maybe resources. Yes. let's open .git ignore. Okay, and then let's create a new folder and call it docs. And here we can have all our readme files, sorry, MD files explaining how the architecture works. So let's go back here. Then have structural source. Okay. Yes, we have 2 ports, okay. Yeah, sure, we don't have stalls, but maybe we have concurrency issues. So it is inherently parallel. Okay, no, it's not split. Both ports have access to the entire memory space. It is not a case of port A getting the lower half and port B getting the upper half. At the silicon level, a dual-port SRAM cell is built with extra transistors. Ah, it's 8 per bit instead of 6. Okay, but yeah, we need to have 2 memories anyway. Consequently, both ports can access any address in the entire range. What happens if I read or write to the same address at the same time? This is called a collision. How it behaves depends on the type of collision. Read or read collision. Port A reads address X, port B reads address X. In that case, there's no problem. Completely safe, yeah. Read-write collision. Port A reads address X, port B writes to address X. In a CPU, this represents self-modifying code. Yeah. Okay. So write-write collision is an invalid state. The memory content of address X will become corrupted or unpredictable. In your CPU, port A would be wired as read-only. Its write-enable pin would be tied to 0. Only port B will have write permissions. Right, because the instruction fetch can only fetch instructions, so this write-write collision can never happen. Okay, so then here I'm going to start creating a new file which I'm going to call memories. Sounds very poetic. Or maybe let's call it VRAM. No, I don't know. Memory.empty. So the memory architecture. It is technically, I think, von Neumann. How is it written? Yes. Architecture. Because I will use just one memory memory cell, memory block. It's not memory block. One memory for both the instruction memory and the data memory. I am going to use VRAMs with a dual access port. Instruction memory will be using port A, which is read only. No. While data memory will be using port B, which is port. Which has read, write, access, launch. Nice. Great. Okay. Here we should have actually some docs about it. So we're not gonna have no, wait, we don't have structural hazards, right? Yes. No, I mean those hazards, I guess. Yes. Because both the instruction, let's close this. IMM and DMM oh my gosh, we'll always have separate hardware to access the memory. We need to be careful to I guess concurrency problems. To read, I mean, read-write conditions. There can't be no right conditions, because the instruction memory is inherently read-only. Okay. That's it. Another cons that the memory is bigger. Let's see how much bigger actually. So if we go here, we search for, did I already open it? No. Documentation. Should be opening somewhere. It's not. I can go here actually. I can search for DRAM. Is it this one? No. I just want a block RAM. Block memory generator. Here it is. Yes. Replaces the dual port block memory and single port block memory logic cores, but it's not a direct drop-in replacement. Should be used in all new Xilinx designs. RAM and ROM functions over a wide range of widths and depths. Use this core to generate block memories with symmetric or asymmetric read and write port widths, as well as cores which can perform simultaneous write operations to separate locations and simultaneous read operations from the same location. Okay, we're gonna see the datasheet shortly, but what if I write memory? Because there is also this one, the DRAM generator. Create area and performance optimized read-only memory. Okay. Blocks, single, dual, and simple dual port distributed memories. So this is all for just for a read-only memory. I don't understand why I'm not able to open the documentation. Probably I didn't install the docnav. Yeah, let me see. Can I search? Doc. No. No, this is not what I'm searching for. Probably I just need to install docnav, which is not here, I guess. No, I have docnav, I guess. Oh my gosh. Let's open the Xilinx Information Center. Yeah, talk enough. It's here, so what is the problem? Wait, I have an idea. I do have an idea. What is happening? Oh my gosh. Yeah, okay, distributed memory, then what? Okay, let's double click here. This is huge, I don't understand why. It's not opening. Why is it not opening? Oh my gosh. This is probably a problem of my Wayland session. Oh my gosh, no. Okay, let's try on Gemini. Hello. I'm trying to learn related match links. Networks. Hopefully. Okay. Why should I? Okay. Sure, I'll trust you, okay. So, if I go to slash tools. Okay, wait a second. What the fuck is tools? I have no idea where my... Okay, it's here. Settings. Yes, let's go here. Let's go to data. Let's see, 2000, and we're already there. Let's go to leap. LMX, whatever that is. Oh my gosh. Okay. So move, leap, STD. There's nothing to that. There is no leap STD C++. Ah, that's true actually. Wait. So here I can go to where is it? Tools, settings, help documentation. So not here. Tools, settings. There is no help. No, it's not working. Docnav to docnav.pin. Okay, like this. I'm gonna do this. So I'm going to go to back docnav. I'm gonna move docnav to docnav.pin. Then I'm gonna make a enough file. Or what is RT library about? Oh my gosh. Where? Oh my gosh. I don't think this is gonna work. Oh, yeah, you're right. I can try to run .nav here. It works. Oh my gosh. Okay, this is cool. At least we can make it work. But why is it not spawning? Anyway, here we can look for there is a ton of documentation here. This Vivado and Xilinx in general are incredible, and AMD right now, but they started doing it. Xilinx, and there is a ton of documentation here, and it's wonderful. It's like the best documentation I've ever seen. So if I search for VRAM finally, actually let's search for memory. Did I do it? It's not. What's the problem? Clear all. Select all. Okay. Now let's look for block. No. So I don't care about Vitis, model composer, Linux. I don't care about IC, IPs. Yes. What is this? Don't care. I don't care. I don't care about this, about this, about this, about this, this, and this. Okay. So let's start from here. IP. Oh, finally. Don't care about the sync ultra scale, but whatever. Oh, single port block memory controller. No, but I want the single port. Let's search block memory for it. Dual port block memory controller. Datasheet. Yes. And let's also open the distributed memory generator. Yeah, I have to open the generator. Discontinued, yes. Block memory generator migration guide, I don't care. Product page, I don't care. Product guide. Yes. Finally. But now, before doing that, I want to see why it's not working. I don't care. I mean, as of now, I don't care. I'm gonna fix that later. So, let's actually see. Let's actually first see the distributed memory. Just look at tables with RAM resources. Distributed read-only memory, single parts RAM. Okay, so you can do both actually. Very large lookup table. Scratchpad memory. Depth. In all support FPGA families, the depth can range from 16 to 65,000 words. Okay. And here, for the block memory, performance optimized memories. Okay, so probably this is faster and supports the AXI interface, which is cool. Supports memory size up to 16 megabytes. What does it mean byte size 8 or 9? What? Configurable port aspect ratios for the... Okay, so this is up to 16 megabytes, so it's much bigger than this. Which is 65,000 words in multiples of 16. each word can be this. So let's say we have a word of 1 bit, which is not going to be, no, it doesn't make sense. That's a word of 1000 bits. So that means that so if we have 1024 bits, they are 128 bytes. If we multiply that by 65,536, this is this amount of bytes. If we divide by 1024, it's 8,000 kilobytes, which if we divide by 1024, it's 8 megabytes. So we could make 8 megabytes of DRAM or 16 megabytes of block RAM. And the performance is up to 450 megahertz here. There's no mention of performance here, I guess. So let's see the dual port RAM. In implementing the most simple dual port RAM, 2 lookup tables sharing a common write logic are used. I don't understand much, but okay. So let's ask for a quick check to Gemini if actually 50 VRAM blocks. Okay, no. So the thing is that the DRAMs are useful also for register development, for making registers, so it's not a really good idea to use them. But the VRAM is specifically designed to use that, to be a memory. So technically, total of 1800 kilobits, which is only 225 kilobytes. So let's write that. Total size 225 kilobytes. So these were just basically the maximum number that Vivado can create. So 16 megabytes of VRAM and 8 megabytes of DRAM. But that doesn't mean that you can create that, because the FPGA is smaller. So this is synchronous, the DRAM is asynchronous, write latency synchronous, performance excellent, highly optimized, can run, God knows what, run at 540 plus megahertz, and this is very slow. Why? Yeah, the block RAM is free in a certain way, because it's not used as with registers, so yeah. Oh yeah, you can use the distributed RAM for the register file. Total, let's say maximum size. Okay. Okay, so decided to go on a unified instruction memory and data memory. Focusing on a table. I then learned about differences between VRAMs and DRAMs, which is quite good, to be honest. Okay, so let's create the VRAM actually. So IP catalog, let's go for the block memory generator. Yes, and let's go and create it. So let's call this the memory, and interface type. Okay, so we now have to see every option here because it's very important. So first of all, generate address interface with 32 bits. Could this be useful? I have no idea. I have absolutely no idea. Okay, cool. I will go on generating VRAM. Given that, I'm using the block memory generator IP for the other. It asks me if I want a 32-bit address. Do I want it? Why exactly 32 bits? What is this? This option enables byte writes, which update the memory content on a byte-to-byte basis. If this option is chosen, okay, so basically you can modify the single bytes. Not sure. Okay, so first of all, it's... What? There's a difference between simple dual port and true dual port. So to see this, we have to go here to see what is the difference. Let's close the distributed memory generator. And let's see. Overview. Yeah, memory types. For dual port memories, each port operates independently. Yes. Operating mode, clock frequency, optional output registers and optional pins are selectable per port. For a simple dual port RAM, the operating modes are not selectable. Okay. Oh, there is performance here. Okay, so the core configures block RAM primitives and connects them together using one of the following algorithms. Minimum area. The memory is generated using the minimum number of block RAM primitives, but data and parity bits are utilized. Otherwise, low power algorithm. The memory is generated such that the minimum number of block RAM primitives are enabled during a read or write operation. Or fixed primitive algorithm. Only one type of block RAM primitive. Why? Well, I would go with minimum area. I really don't care about power, so this is not an embedded project in the sense that it needs to go on run on a battery, so we don't care about that. So actually, let's do this. target algorithm, minimum L. Okay. Okay. Then, yeah, let's see what it works. Do you want a physical 32-bit address on the game? No. Not unless you're using an AXI interface. If you're using a native VRAM interface, you should let Pivato calculate the address width automatically based on the memory size you choose. But as the CPU uses 32 bits, because RISC-V is a 32-bit architecture, no, it's not the reason why, because there's no RISC-V architecture now. If you should make your VRAM 64 kilobytes in size with a word width of 32 bits, your memory will hold 4 bytes per word, 16,384 words. Okay? You only need a 14-bit address line. If you configure the block memory generator in native mode, you will enter 32, yeah? That will automatically calculate the address width and give you a VRAM IP, a 40-bit address input. This is the most common bug people encounter when building their first RISC-V memory interface. RISC-V is byte addressed. Every unique address in RISC-V points to a single 8-bit byte. Because instructions are 32-bit, the program counter increments by 4 for every instruction. Yes. VRAM IP is word addressed. The block memory generator expects word addresses. Okay, no, wait a second. Yes, because RISC-V requires it. So, first of all, let's go. I didn't actually read what is the difference between the two. I will read about that later. Now I want to read about different kind of memories. Memory types. So Write collision example from content. Write enable A. Well, common clock, I guess, yes. I did not understand much from your explanation. So I should select byte write option, I guess. And what is best between using native interface and XC4? Also, what is the difference between simple word part and true word part? And should I use parity bits? What is ECC? Since it's starting to hallucinate, I might want to actually I don't know, copy this and then switch. I will switch to a better model. Should you select the byte write option? Yes. Okay, so byte addressable, yes. No, it's not byte addressable, but single byte. Writable, I guess. Simple door port versus, oh no wait, native interface versus Axis4. Choose the native interface. This is just a set of simple direct wires, address data in, data out, write enable clock. It's very easy to connect directly to your CPU code. Okay, let's use native then. Simple dual ports versus true dual ports. A simple dual port, you have two ports, but they are specialized. Port A can only write data, and port B can only read data, which is perfect. Okay. So, simple dual port mode. Port A can only write, port B can only read, which is cool. A true dual port, both ports can read and write independently. Yeah, which is not ideal, because it is exactly what we want to avoid. Because we want the instruction memory to be only with read access, and the data memory to be both. But wait, port A can only write and port B can only read. True dual port. Port A instruction fetch only needs to read. Port B, because port B needs to do both, simple dual port won't work. Ah fuck. Since it forces one port to be read-only and the other to be write-only. You need true dual port. You would simply tie port A, write enable Y to 0. But wait a second. Okay, wait. I have a question about this later, but let me first read this. Parity bit no. A parity bit is an extra bit added to the data to check if a transmission error occurred. Your CPU and VRAM are both inside the same FPGA chip. The connections are physically silicon traces. They are extremely reliable. Parity just adds extra wiring complexity. Okay, so I trust him. No. ECC error correction code is an advanced version of parity. If a bit in memory gets flipped due to background radiation or a power surge, ECC can automatically detect and fix the error using server RAM, space satellites, and critical medical equipments. Okay. Error correction code ECC. No. I can actually make a table for this, but I will do that later. Let me actually see. Oh fuck. Yeah, didn't think about this. Did not see this coming. So but why can I not just use a simple dual port VRAM, and when I want to write data I can just use the INAN port. Sorry. The write or data. Instruction fetch stage needs to read the next instruction. Memory access stage needs to write data to memory. This needs to read data from memory. Okay. Imagine a CPU is executing a program. In the exact same clock cycle, the CPU is fetching an instruction from address 0x0304. An earlier load instruction is in the memory stage, trying to get a variable from address 0x1000. If you're using a simple dual port PRAM, port A cannot be used. Oh wait. An earlier load instruction is in the memory stage, trying to get a variable from address 0x1000. If you're using a simple dual port PRAM, port A is write only, cannot be used because neither of these two tasks is a write. But port B is your only option. Okay, yeah, you cannot use the simple port dual RAM. Sorry, simple dual port PRAM. So now through dual port modes. So both ports can read and write. Careful. With true dual port, both port A and port B can read. You permanently connect port A to the instruction fetch stage, but you just use it to read, and you permanently connect port B to the memory stage. Let's remove this careful. Port A always reads the INAN. While port B can do both for the INAN. I want to put this in a table, but I remember how to do tables in Markdown. Okay. How the fuck do I do it? How do I close the table? I do not. Okay. This is quite ugly as a table. But whatever. So okay. Yes. Nice. I like it. It's quite cool, to be honest. Okay. Okay, great. So we can continue. No ECC, byte rate enabled, no parity bit. So 8 minimum area, native true dual port. Common clock, yes. Generate others interface 32 bits. No, I don't think so. Yeah, we can put this here. Here. Okay. So common clock. We can put, I don't know. We need to check actually. What about common clock and okay, so write width, it's gonna be 32 bits. Same for read. Write depth. Well, I guess we can go with the maximum. What do I start with for the depth? Do I use the entire space available? What about cut surface? Write first, read first, and change. Ah, yeah. In March. Enable printing. Primitives output register, core output register. Register CAEA pin. There is a lot of stuff. Reset the synchronous pin. Okay, that's all for now. Getting quite sleepy. So, common clock, yes. Yes, makes sense. Okay. Memory depth. Start with a depth of 16,384. 64 kilobytes. Or 80,192 words, 32 kilobytes. Do not use the entire space. The Basys tree has 225 kilobytes of VRAM. If you use all of it for your main RAM, you won't have any VRAM blocks left for other features, like a video frame buffer for graphics. Ah, fuck. 64 kilobytes is more than enough for assembly programs and small C codes. Yeah, but this is going to be also... Okay, whatever. let's go with maybe 30 kilobytes for now. Oh fuck. Okay, so P total available memory is going to be 225 kilobytes. Yes. For now, we're gonna go with 32 kilobytes, which is equal to I don't know. Okay, 32 kilobytes. That's right. Let's wait. Then no. That's right. Width is going to be 30 bits. Depth. Well, to make 32 kilobytes, we need I don't know. So we have 32 bits. They are whatever. They are 4 bytes. So to make 32 bytes, 32 kilobytes, we need to make the logarithm. So logarithm base. How can I change the base? Fuck. Logarithm base. Oh my gosh. Base 2 of 32 kilobytes. Oh, I mean, this is gonna be 5. Okay, then this means that I don't know what I'm doing. I'm actually stupid. So 32 kilobytes is 768 bytes. Can I use the normal calculator, please? Okay. Yes. Oh my gosh. I just want the standard calculator. So let's start again. So 32 kilobytes times 1024, we have 32,768 bytes. If we divide by 4, this means 192 lines, memory lines. The depth is not in bits, but it's in, I don't know, lines, side word lines. Yes. So here write depth is 8192. Why the read depth is 16? I have no idea. I have absolutely no idea. Okay. That's the same here. Okay, it's the same. Read width. Yes. Operating mode. Common clock, yes, of course. Read first, sometimes called read before write. If the CPU reads and writes to the same address at the exact same time, read first ensures that the read port returns the value that was in the memory before the write started. This is a standard behavior expected by most CPUs pipelines. Right. It's corruption. Okay, yes. I mean, what is the difference between these two registers? Optional output registers. The block memory generator core provides two optional stages of output registering to increase memory performance. The output registers can be chosen for port A and port B separately. The core supports embedded block from registers as well as registers implemented in the FPGA general interconnect. Okay. And then we have optional pipeline stages. The core provides optional pipeline stages within the MUX, available only when the registers at the output of the memory core are enabled. And the block memory generator core allows optional pipeline stages within the MUX, which might improve core performance. Users can add up to 3 pipeline stages within the MUX, excluding the registers at the output of the core. Each pipeline stage adds an additional clock cycle of latency. Okay, so I don't understand, wait. I'm not exactly sure what this is used for. Okay, I will see that later, but anyway, so we're not select also the register CEA. No. Then reset asynchronous. No, it's just a reset. I think we need that, right? Uncheck. You don't want a hardware reset pin that wipes the entire memory to zeros. Instead, you initialize the RAM with your program code. Okay. So we don't need a reset parent. No. Where's the priority? It's useless. That's it. But why? I did not exactly understand why what the primitives and pipeline registers are used for. So here, in the meantime, is enable pin read first. We don't need this, and we don't need this. Port B. This also read first. Oh no, wait. Same, yeah, read first. Yes. No, we don't need that. That's it. I guess it's everything. Nice. I'm just using 8 block RAMs and I have 50. Okay, no output registers. You give the VRAM an address and the next cycle the data is out. With a primitive output register, you give the VRAM an address and data comes out and saved in a temporary register inside the VRAM clock. Cycle 3, the data travels and there's your CPU. With a core output register, this adds another layer. But why? Oh. Okay, yeah, we don't need that. Great. So at this point, we can generate it. Yes. 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 So let's go. Let's run it on 2 jobs because the other one to cook my laptop. And let's go. Yes. So here now it's generating the design, which is called memory. No. And then I can start to unwind everything and to log everything that I did for today because I'm going to go to sleep. So let's see here if everything's alright. Yes, this looks very cool. The run is successfully completed. So we generated our memory, which is the first stage. So let's go here in the let's close this and this. In the log, what did I do? Generated 32 kilobytes VRAM. More info in docs memory.md. They want to do. I guess we can turn this into tasks and to-dos. So yeah, I guess we can check this and this not really. So I can also write here what do I want to do next. And what I want to do next is just this. Continue looking at plan.empty and make architectural decisions. That's it. This is the single most important thing that I want to do. And then everything else is just gonna follow by itself. So, I can write here that this was a Friday. Is it important? Yeah, why not? That's it. I think I can just commit everything I did. What is this exactly? Something that I probably do not need, but let's add everything. Okay, and then I can write commit message, which can be something like I don't know. I'm very bad at commit messages, to be honest. Just gonna generate it. Yes, perfect. Very concise. And let's push this. Yes. Great. Nice. So, I guess for today it is everything. I really had fun, learned a lot during tonight, and I'm gonna go to sleep. Good night, everybody.